Okay, so we just introduced something that, as I said, tends to make people's heads explode a little bit. It's the idea that when you take the time derivative of r hat, you get theta dot theta hat, and when you take the time derivative of theta hat, you get minus theta dot r hat. Um, this, looks really cute and it's really compact, but what the hell? What does that mean? How does that work? So in this video, my intention is to just try to help you think about why this is, besides the fact that when you do the math, it comes out that way. Certainly when you do the math, it does come out that way. We just saw that in the previous video. But in this one, I just wanted to try to provide some ways to think about why that happens. Okay? So the first way I want to think about it is to think about cases where theta hat and r hat don't change. So let's think about motion where theta hat and r hat don't change. So case one, theta hat and r hat do not change. And boy, if I could keep things actually on the screen, that would probably make it much more useful for you in trying to see what's going on. Okay, so what's an example of motion where theta hat and r hat don't change? I'll propose one. What if I've got some object, a car or a fly or a rocket ship or whatever the hell it is. It starts here and it moves out along the x-axis. Now, if you think about this object moving along the x-axis, when it's here, r hat is pointing the I hat direction, and theta hat is pointing in the j hat direction. And the same thing is true when it's here. R hat is still pointing in the I hat direction. Theta hat is still pointing in the j hat direction, right? So pretty clearly moving out along the x-axis, r hat and theta hat are not changing, right? So you would say for this case, here, d by dt of r hat is 0, and the reason it's 0, it's because it's not changing. So the motion is such that r hat is not changing, right? Same would actually be true for motion when I'm moving along the y-axis, right? R hat in this case is always up, theta hat is always to the left. When I'm moving in the negative x direction, right, r hat is always to the left, theta hat is always down. And simply if I were starting here and moving directly away from the origin, r hat would always be pointing outward and theta hat would always be pointing in that direction. So for each of these motions, r hat and theta hat don't change. I'll note that there is one sort of very funny thing that happens here, which is if you go through the origin, something weird happens, right? At this point, r hat is pointing in this direction. When you go through the origin, r hat and theta hat both go through a discontinuity, so r hat was pointing this direction, theta hat was pointing this direction, and then you go through the origin and flip. Theta hat is pointing up, r hat is pointing out in the other direction. So we need to be a little careful with the origin here. But setting aside the origin, these are all motions where r hat and theta hat don't change. And now, it might be tempting to say that's true because it's moving in a straight line, but that's actually not why r hat and theta hat don't change. So let's think about this case. Object moving in a straight line, like so. Here's my origin. Now, if I think about this case, right, when the object is here, r hat is pointing in this direction, right? Theta hat is pointing in this direction, right? By the time the object is over here, r hat is pointing in this direction, and theta hat is pointing in this direction, right? And these are supposed to be at right angles because they're always at right angles. So pretty clearly, it's not that it's moving in a straight line, or it's not simply because it's straight line motion. Straight, how the hell do you pronounce that? Not simply because it's straight line, but rather it's because theta is not changing. Okay? So for this motion, theta stays the same the whole way out, right? For this motion, theta stays at 0. For this motion, theta stays at pi over 2. And since theta is not changing, the direction that points away from the origin is always staying the same, right? Which is what r hat means. So r hat, which points away from the origin, stays the same. And theta hat also stays the same because theta is not changing, so the way that you move to increase theta stays the same. And theta hat does too. Okay? So this is sort of one way to get some insight back into this idea that you need theta to be changing in order to get a meaningful time derivative of r hat and theta hat, right? When theta is changing, right, then dr hat by dt has a non-zero value. If theta is constant, dr hat by dt is zero because theta dot is zero. Okay, so this is sort of a way of explaining why it is that theta dot shows up here. The reason theta dot shows up here is because the only time when r hat or theta hat change direction is when the angle is changing. So of course the other question here is not why does it depend on theta dot, but also why are the directions what they are? And there's actually a fairly simple answer for that, which is that those are the only options. Like if you ask the question, in what direction can r hat change? Well, there are only two direction options in the polar coordinate system. One is in the r hat direction and one is in the theta hat direction. Wherever you are, right, you could either move in the r hat direction or you can move in the theta hat direction. Well, if the direction of r hat is going to change, the only option is for it to change in the theta hat direction, right? It can't change in the r hat direction because then it's not changing. And by the same token, the only direction in which theta hat can change is in the r hat direction. So in some ways you can look at these and make a lot of sense of them. They say that, first of all, r hat only changes if theta is changing, and r hat has to change in the remaining direction that it can change in, which is the theta hat direction, and vice versa. Theta hat changes when theta is changing, but has to change in the r hat direction. The signs take a little bit more thinking to get nailed down, and I'm not going to spend time thinking about those or talking with you about those. But if you're confused about why the signs are what they are, there are also some good explanations for that as well.